Topic is about valves and the impact of the control valve characteristics on installed flow measurement. This is a plot of a typical response curve of the valve CV versus valve lift for various types of valves in industry, linear, equal percentage, and quick opening. These valve characteristics are obtained with a constant dP over the control valve. So these are ideal world conditions. Unfortunately, in the real world, the valve is part of a larger piping or network system, which means that the resistance over the valve is a function of the entire network topology resistance, which results in distortion of these response curves.
A quick overview of control valves. In the main control valve shown in this extract from the Emerson Control Valve Handbook is a globe valve. In the top you have the three different cages that can be used, examples of them, different port openings to give you the different characteristics which are shown on the top right hand side. The equal percentage linear and quick opening as previously discussed. Globe valves sometimes have noise reduction cages around that cage for a high pressure loss. Typically, if you're venting steam from a high pressure to low pressure, then you have a noise reduction cage over the cage. Bottom right hand side is a conventional butterfly valve, which normally gives you a quick opening characteristic, and on the bottom right you also see a triple eccentric butterfly valve, which is quite a specialized valve. I would recommend reading up on that.
So the next thing to look at is the installed characteristics of control valve, which is a process modeling problem. On the top left are the normal or typical response curves of three different types of valves, linear, equal percentage, and quick opening. The equal percentage is the CV max times R, which is R some kind of factor to the power of x minus 1, where x is the valve lift in the fraction. Now, the problem with that particular equation is that when x is 0, you get CV over R, which is a non-zero intercept. Now, a non-zero intercept is an issue, especially if you're trying to model plant data, because at zero valve lift, you should have zero flow. So I modified the equation to include the valve lift or valve fraction added into the entire equation. In other words, merging the linear and equal percentage equations.
So if we have a look at the problem, we have two pressure losses or two resistances in series. The first one is your valve loss, which you can get from rearranging the subject of the equation. And then the pipe loss, if one assumes that the flow is proportional to K times the square root delta P. Then if we get the total line losses, it's the sum of those two pressures. And then if we look at the discharge pressure of the pump, and we assume it's a polynomial, what we need to do is solve for the pump discharge pressure, or for the flow where the pump discharge pressure equals the required discharge pressure. In Visual Basic, this can be achieved using an interval halving method as shown here, assuming it's a polynomial for the pump performance curve. So here's the Excel document where I have put polynomial, assume the 200 kPa discharge pressure of the pump, which is pretty low for a single stage pump, and there's a pump curve, as you can see, which is typical for a centrifugal pump. If you flow versus pressure, normally it's a little bit flatter on this section. Now what I want to work through is how the selected characteristic and the actual installed characteristics is distorted as a function of relative losses in the line. So we have the equations as discussed previously. And what we have on the right hand side here, this is the valve opening and this is percentage of total flow normalized. So we've chosen a linear valve as shown here, and for this linear valve, the actual installed characteristic for a constant conductor or resistance of the pipe, this is the actual installed characteristic for that pump curve. And you can see in the plot below here at various valve openings what the flow would be. So we would normally obviously design for 80% valve opening, so and that would give you a sort of, it's a 61% line loss over the valve. Now, if we want to see the effect of increasing the CV of the valve, we can increase the CV. In other words, we're reducing the losses over the valve, and you'll see what's basically happening is the line is distorting even further to give you more of an equal quick opening characteristic. If we go now back to even lower, if we make it highly restrictive, it almost goes back to the design case, but we can't get the flow we need through the valve. So it's a bit of an issue. So CV of 1 is pretty much where we need to be, and we're now looking for, we want to get an installed characteristic which is linear. Now, with an R value of 1, you get a linear. If you decrease R, it's going to become more of a quick opening characteristic. So decreasing R, you can see we're just making the whole problem even worse. Unfortunately, when R goes that we go over 100%, it doesn't solve properly. Taking R back to 1, it's a linear valve. Now if we make it equal percentage, the more equal percentage we make it, and we can increase the CV. So as you can see, we can actually almost get to a point where we can design for almost linear installed characteristic with about 30% loss over the valve, which gives you for most of your flow. So this is the importance of selecting a valve, keeping in mind the actual total installed characteristic. Now that we understand the installed characteristics of a control valve, the next problem is flow measurement turn down and controlling that. This is an extract from Liptak's book on flow elements. You will see it gives a good idea of what range you could work with for a given type of flow meter, as well as the rangeability or turn down of the flow meter. And that's quite important to understand. We're normally working with orifice plates. It talks about a 3-to-1 turn down. In other words, it's designed for 1,000 units per hour. At 333 and below, it's going to start becoming more and more unreliable to the point where you're going to get a very, very noisy signal, or it's going to go to zero. So the turn down is quite important to understand. So this is also an extract from the second page, where you can see additional flow meters. More expensive ones can give you fairly high turn down. So the question is, from real life plant data, what does it look like in terms of the flow versus valve lift? Here's an example of some plant data. There's a graph of the valve lift versus the flow measurement. This is for an orifice plate. You can see the installed characteristic is looks like an equal percentage installed characteristic, and at around 25 to 30% valve lift, we're in a region where the turn down of the flow measurement is such that we've got this high degree of noise, which is seen by this noise band, and then in regions which I've cut off below 20% becomes unreliable. Normally, you have two options that you can configure in systems. You can configure to freeze at a value which will be above 0, or you'll have the noise in the signal. So now, based on what we've shown already, the idea is to try and see if we can fit a curve fit through here so we can get a good idea of how to estimate the flow in this region over here. This is where we don't know what the flow is like. So using solver, one can use the equation that I had previously, and you're trying to minimize the sum of the square of the errors, which is, here's the actual measurement, and there's the curve fitted measurement. There's this CV value and R value, defaulted values to 1, and using solver inside Excel, unfortunately this is going to take a while to paint because of the data, but we want to minimize the sum of the square of the errors by changing cells F1 and F2, which is this. We allow that to solve. And what we're looking for at the end of the day is almost a straight line through here, which is what we are seeing. And so it's done a very, very good job of curve fitting. It's got a 99.79, 98% correlation, and slope is almost 1 if we look at the measure versus fitted flow. So it's a very, very good curve fit, which means we now have an equation which can determine or estimate the flow in this region over here if we know the dP over the valve and the valve lift at that time. Here's the characteristic, or here's the solved value is 0.5 as theoretical, well, CV, artificial CV, and R being 9.7 shows that it's a strongly equal percentage valve.
Now, another way to look at this problem is to reorder it or change it by logging both sides of the equation. If you log the left and right side, log of flow over square root delta P, and the log of CVRX, and you move the log of X to the left hand side, you end up with a linear equation where you have the log of the flow over square root of delta P minus the log of X equals some linear function of X. So you can basically see it's Y equals mx plus c. The Y values can be calculated from plant data, and the X values are known. So the trick is then to take that data, calculate the Y values from plant data, and plot that, or compare it to X. And if you use built-in equations in Excel, you can then use those to calculate the slope and the intercept of the X and Y values. And you have, in essence, two equations, two unknowns, and fairly easy to solve for. Solution can be found by using the two built-in functions, slope and intercept, which are used in Excel, and you can see on the top right hand side there. For the original curve fitting using solver, CV was 0.543, and using the linear method 0.532, and R was 9.743 versus 9.438. So you can see it's a lot simpler.
And there will be times where you have data without a dP over the valve, and you have an example of valve lift versus flow, and you just really want to fit a line that goes through the origin or some description, just so that you can get a good estimation of the flow at low ranges or high turn down. What I normally do is, if we have the valve lift and flow, this is quite a clean set of data. You can download or purchase an application called Curve Expert, and inside Curve Expert you can add your own you can add your own user model. So I've created a user model here, which is poly origin, which is a quadratic which goes to the origin. And gives a very good fit, or we can tell it to go through all the models and decide which one is the best. That still comes up with the user-defined model. I see the information is there. Copy that equation. We have the equation. And you can see it's very good curve fit. So now you've actually just got a quadratic equation, which does exactly what you need.